Take it away, Tectonic.
Hello, we are Tectonic, and we are Group 547Q, composed of Derek Colon, Ryan Edwards, Colby Farron, Ria Fettig, Rachel Jones, Michaela Judah, and Cyril Morin. So the agenda of today's presentation will be as follows. Our shaker table designs key specifications, the endurance testing of our prototype with videos, design highlights and features unique to our table, the evolution of our design, CAD diagrams and exploded views of our subsystems, a cost table summary, software features and implementation, and at the end, we will open the floor to questions. Next slide, please. So for our key product specifications, our shaker table is 10 inches long by 13.5 inches wide by 7 inches tall. We provide motion in both the X and Y axes using a timing belt pulley system driven by two NEMA 17 motors. Our table has an easy-to-use control panel with a larger LCD screen and an LED emergency shutoff button for safety. And we provide 3 operating patterns with adjustable speeds and radii of up to 400 RPM and 25 millimeters respectively. Next slide.
Okay, so here we have a picture of the LCD screen and the overall shaker table. The major issue with meeting the requirements for the endurance testing was that we never got in our linear guide rails from IGUS. So since we never got them in, we had to 3D print them, and the 3D printed ones had a very high friction, and they only worked with 2 of the rails on, because if we put all 4 on, then it didn't move at all because of such high friction. Since there was so much friction, the orbital started to drift, so we had to recenter every so often, depending on the type of orbital. And then as we've seen in the LCD screen for this picture, the dial was able to go to 2 weeks, which was the requirement. But however, it would start to shift and we'd have to recenter every so often. So after we never ran it for 2 weeks, obviously. So we never actually saw where it would be at 2 weeks, but it would run for 2 weeks, hypothetically. Also, due to the friction, the plastic rails worn down unevenly, so that would also lead to drifting of the 2. Next slide, please. So here we have the actual working shaker table. So the red button turns it on, and then you can cycle through your 3 different types of orbits or patterns. So this one's double orbital. Set the RPM to 300. Our max RPM was 400. And then the days goes up to 14. The hours goes to 23, and the minutes goes to 59. And then set for 20 minutes. And here's the calibrating. So it calibrates by going to the bottom left corner in the image or in the video and clicks the limit switch. The second motor moves very slowly due to the friction on that motor, or on that side, on that rail specifically. So once the calibrating done, it centers in the middle, and then it does the double orbital pattern. And we were able to see that the double orbital pattern worked very efficiently because we stuck a pencil to the center block and we drew it out, and it looked just like a figure 8. After about an hour, the pattern begins to drift. So after every hour, we recenter it. The requirements were 150 cycles per minute for 20 minutes. And from the video, you can tell that we met this requirement even with the added friction. Next slide, please. Here's our linear pattern. As you can see, it obviously goes very slow. So it doesn't meet the 300 RPM requirement. But this was because when you only have one of them moving, the other rail starts to twist back and forth, and it caused the center block to be at an angle, and so it can't slide properly. So this one actually has the most friction, and so it moves slower than all the other ones. We're hoping that we get the IGUS rails in time to run these endurance tests by Friday, so that we can actually see it run with the rails and hopefully make sure that it actually works with the proper rails. Next slide, please. Here's our orbital pattern. Again, we were able to see that it did perform a circle based on putting a pencil to the center block. It was able to also meet the 300 RPM requirement. However, with this one, it drifted much more than the other one, so we had to recenter about every 10 minutes. Yeah, next slide, please.
All right, thank you, Ryan. So now I'm going to get into some of the features of our design, which make our design unique from the others. So the first of these features is our rail and tensioner subsystem. This is essentially the building block for which the rest of our table will function off of. So here we can see that we have 4 IGUS rails. On the right side, you see these, and they're all perpendicular to each other on that base plate. And then on these rails, we have 6 IGUS pillow blocks, 4 of which slide back and forth to drive the system. Those are in the middle of the rails. And then the 2 other pillow blocks are attached to the tensioner system, which you could see in the expanded photo on the left. And these tension the belts with those bolts that you can see there using those pillow blocks. Next slide. Okay, so the next feature of our design is the pulley and center block subsystem. Again, we have 2 NEMA 17 motors, which drive these belts, and you can see that the motors are orientated at the corners opposite from each other and attached to the motor adapters, which drive the belts. And then you can see the center block in the middle is attached with the rods through it. And then in the expanded photo on the left, you'll see the belt clamp, which uses 4 screws to hold those belts in place. Next slide. Here's our well plate and tube rack holder, which is actually modified. So we created it ourselves. And it essentially uses 2 adjustable thumb screws to hold those well plates and tube racks in the middle. And it also has, to hold it to that center block, 4 screws in the middle, which are countersunk. Yeah, and we'll see a 3D printed version of this on the next slide. So here's that 3D printed version. In the end, we hope to have a manufactured version, which would be more effective. But on the left here, we see that the well plate is being held by those 2 adjustable screws. And then on the right, we have the tube rack being held in. Next slide. So this is our user interface subsystem. On the bottom right side, we see the emergency stop button, which when pushed in, turns off the power. And then to turn the power back on, you just twist the button and it pops out. And then the LCD screen is then powered on. So this LCD screen is positioned in the middle, as you can see, and has all the program commands on it. So to control it, we have the potentiometer and on the far left side on the bottom. Essentially use the potentiometer to scroll through the various programs that we have for the patterns. So linear, orbital, double orbital. And you then press the button to go to the next phase, which is picking your designated RPM, and then click the button again. You can go to your runtime, which cycles through days, hours, and then minutes. So you can pick how long you want to run for. And then the other feature is if you hold down that button, it will stop the system and return you to home, so you can reprogram to another orbit that you might designate or want. Yeah, so next slide.
In the early stages of our design process, we first came up with an idea to utilize lead screws that are connected to motor shafts, and these use bearings and blocks to move the center block back and forth. And these are perpendicular to one another such that it can achieve 2 degrees of freedom and the 3 different shaking patterns. Now, once we came with this idea, we performed some preliminary analyses, and we found that the torque that this system will be able to provide would be sufficient for all the static inertia of our loads and everything. But in order to achieve the 350 RPM that the customer required, we would need lead screws that would have more starts and would have more leads. And after doing some research in the market, we found that this would be way out of our price range and too expensive to implement. And so we figured out that we have to do something else. Now, as you see on the right, this is our second iteration. And for this, we went a more simple approach, and we just use a belt and pulley system. And it is essentially the same concept of movement, where we have these 2 motors moving these belts which actuate the center block and thusly the well plate holder in different patterns. And as you can see that the belts would be able to achieve a much higher RPM for a much lower cost, but in turn we would lose some torque, which was acceptable. And we found that and we calculated this would be able to achieve 350 RPM as a customer required. And as you can see on the top, our first iteration of the well plate holder, we use 4 lead screws that the user operator would twist in order to secure the well plate or the conical tube rack. And this was variable to do many different sizes that the customer had. All right, next slide. And this is our final iteration of our design. As you can see, we decided to stick with the belt and pulley system to actuate a shaker table, but we did have a few adjustments to the UI, to the controls, and to the well plate holder. As you can see here that the well plate holder now only has 2 thumb screws, such that the user doesn't have to, twist 4 of them to secure something in place. It also has that little lip on the edge, that little rising to secure the conical tube rack. And the one difference with this that is pretty significant is that this restricts it to the conical tube racks that we manufactured. So the user can't use any of those. And additionally, in this design, you can see our UI and control system where we have the LCD screen, the stop, and the potentiometer and the dial to switch it all. And this is how we integrated everything. All right, next slide.
All right, so I'm going to go ahead and go over some of the unique and key features that we have here on our design, and I'll address them in a little further detail. So first up, we have the motor pulley interface, which is something we included after upgrading from our lead screw design as we just covered. So it's part of the larger motor subassembly, and there's 2 of these on this design. And it's responsible for transferring obviously the power from the stepper motor to the belt pulley system. So here's just a cross section showing kind of what's going on in there. So the main design hurdle we had with this portion of the full design is that the stepper motors we used have a 5mm D profile shaft. Those are the off-the-shelf ones. And based on the width of the belt and the belt that we chose, the best pulley we could find had an 8mm internal diameter. So we used a 5mm to 8mm coupler with set screws and a custom machined D profile shaft, which I'll go ahead and break it down there a little further with some isometrics. So beyond just being a way to bridge these 2 diameters, the function this serves is it actually elevates the belt off of the rail system that you've probably seen. So this gives us that space and kind of keeps things from conflicting within the bottom part of the design. So next up is the Pulley-Tensioner Interface. So this is the other end of the pulley belt system. And the way that it's different, obviously, from the other one is that instead of providing power to the belt, it's just rotating freely and trying to minimize friction. And we have a series of bearings that kind of buffer it and make sure that it rotates best as possible, that it's not a big point of friction. So I'll start from the top and just break down all the components here. As you can see, this is affixed onto the greater kind of tensioner subsystem, which is on the rails, and that's kind of been gone over already. So up top, we have the M6 socket head screw with the pretty long shank that basically makes sure that none of the threads are loaded in shear because of the belt tension. And then below that, we have the flange nylon sleeve bearing, which goes directly into the pulley. And then we have our 5/6" width belt, and then our pulley. And then on the bottom, we have our other flange nylon sleeve bearing. So the added benefit of these sleeve bearings is they also kind of act as an insert into the pulley, because as we know, the pulley has an internal diameter of 8mm, and then obviously the M6 bolt has a shaft or a shank diameter that is much smaller. So there's a little bit of space there. So these act as inserts. So basically, when tension is placed on the pulley and there is torsion on the full subassembly, the inside of the pulley won't interface with the outside of the bolt. So that's another way it reduces friction. And then on the bottom, we have a roller bearing, which minimizes friction between the bottom of the pulley and the top of the tensioner subsystem, then a washer below that to give it a flat surface. So next we have our 4 belt to shaft connectors, 2 for each shaft we have going through the center block. So on the bottom, you can see that they have belt clamps, and they interface with the rods. There's in the center block, they're stacked on top of each other. So they all need to be unique. They all need to have different heights that they hold the shafts above the base plate. So I'll just break down this one. They're all relatively similar. On the right, you can see a little closer and more in depth our clamping mechanism. We have 2 metal clamps that go into the grooves in the teeth of the belt, and you don't have to tighten down the screws so much because of those teeth. And then on the left, you can see the mechanism with which the clamp actually clamps down onto the shaft by tightening the bolt up top.
So this is the overall movement subsystem for our shaker table. So when the motors spin, the belt moves around the pulley and allows our system to move. These belts are connected to brackets using a belt clamp, and these brackets are connected to our pillow block bearings that slide along our linear guide rails. The center block in the middle is connected to our brackets using shafts, which allow our center block to move when the belts move. Next slide. So this is a top view of our movement subsystem. So there's limit switches in the corner that allow for homing of the system, and the system is capable of linear, orbital, and double orbital patterns. The pillow block bearings slide along the guide rails, and the brackets that sit on top of these bearings are connected to the shafts that connect to the center block. This allows the center block to create the desired patterns when the pillow blocks move. Next slide. So this is the cost required to create one prototype of our system, which is $354.54. The majority of this cost comes from off-the-shelf parts, and one way to reduce this cost would be to look for cheaper alternatives to our pillow block bearings and our linear guide rails, because these were our most expensive off-the-shelf items. Next slide.
For the software features, as discussed, we have 3 different programmable patterns, so linear, orbital, and double orbital. Within that, we can run anywhere from 100 RPMs to 400 RPMs. Our durations go from a minimum of 1 minute to 14 days. And our distance or radius, so this is from the center after we homed, we can move from 5 millimeters to 25 millimeters from the center. To fix our issues with drifting, we have some software features where we recenter every 10 minutes to an hour to account for drift depending on the pattern. And also we recenter if the limit switches are hit during movement, which is instant feedback that we've drifted too far. Additionally, we display our current pattern and time remaining in minutes. However, under 3 minutes, we start displaying the time remaining in seconds. Next slide. For software implementation, we use Arduinos. We use a multi-stepper Excel library, which can be found online. For orbital and double orbital, we achieve this pattern by iterating through a 2D array of desired positions. Both motors must reach the desired position before moving to the next desired position. And the positions are determined based on a unit circle. Additionally, we check the bounds at the end of each movement. So as you can see in the for loop at the end, there's a function called check out of bounds, and that's to see if we've hit the limit switch. Next slide. In conclusion, Tectonic's goal is to provide efficient material selection, increase ease of use, high levels of safety, and responsive shaking patterns to our shaking mechanism design. Thank you. Next slide. Are there any questions?
Okay, sorry, that was me transitioning from my my cell phone to my computer, and Dr. Nemi is literally putting out a fire. There's like a fire right there that he's putting out. So, hey, your IGUS rails came.
That's good.
Let's go.
Yeah, they're right here.
Don't lose them.
So
Wow.
yeah, I'll just toss them back here, and so they came. So this will give you guys hopefully a solution to all the friction and wear and all that stuff that you guys were talking about in the beginning. But I guess well, so here before I jump in and start barraging you with questions, let me ask if there's any questions from our panel, which I think is, well, Dr. Nemi is literally covered in like fire extinguisher stuff right now. So from Alex, who I guess is the other panelist.
Hey, so first of all, good job, guys. You know, I think so far, at least from what I've experienced, that this has been the, how do I put this? The most fluid presentation, I want to say. It felt very smooth. There was like very minimal breaks. It sounded like it was very well prepared. So good job on the actual presentation portion. For your cost too, is this cost projection of the $300 some counting the IGUS rails? Because this by far is the cheapest shaker table from what I can recall out of the presentation so far by like a significant margin. Dr. Trong, correct me if I'm wrong, but I'm wondering how at least.
Sorry, can you guys bring up the cost slide so that we can see the breakdown?
It seems odd that the other ones have been around the same general range, and then yours is just unbelievably cheaper.
Yeah, it includes the IGUS rails, but it doesn't include like parts that we got from the lab. So like the motors, and we ended up using like a lot of screws and stuff that we just found in the lab instead of ordering them.
Okay. Do you have like a general cost idea of what your shaker would cost, including everything?
Like if we ordered all the different screws.
Yeah, so like the general, at least from how I view this, if you were pitching this to, you know, the sponsors that would go and, you know, either buy this from you as a brand new product or go make it themselves, you know, they would need all of the parts, including the parts that they don't have access to from the Mech 3 lab. So I'm wondering if you have a cost projection for, like, you know, if you were to go actually make this starting from nothing.
Yeah, I would have to go back and look at the PO because I took them out of it, but I have an old copy somewhere. I would just have to add back like the motors and the screws.
Okay.
Also like electrical components that we ended up just getting from the lab.
Okay.
Okay.
Oh, that was it for me.
Okay. So
I'm back.
oh,
Kind
okay.
of, sort of, momentarily. I'm still putting out fires, but
Well, you can ask her. Or I was going to tell a war story that leads to a question.
can I ask?
Yeah,
Well,
go ahead. I'm here.
So yeah, so your design, if we go back to like a picture of the full assembly, like that's fine right there. Did you guys notice any, you mentioned the migration you had where friction would cause it to slide along. When you were getting it running, even for the orbital or just the linear where friction would have been as much of a concern, did you have any wobble of the table? Like, because it looks like an inverted pendulum from the side view. Did you notice any wobble there, or was it rigid? You understand what I'm saying?
Like wobble is in like the top plate holding like
The top plate following an arc instead of purely translational motion.
I can't say I have noticed that. I
I don't think we
wouldn't-
ever experienced that.
Okay. Yeah, I was just looking, you've got a mass on top of a block, and the block is constrained at its bottom, and the mass is on the top of it, and it's like, all right, cool, well, it's being driven and constrained down here, so it could be rocking, and I was just curious if you I noticed any of that, or if it was rigid enough to not have that issue. So it sounds like it was rigid enough to not have that.
I think maybe if that'd be a problem with like the actual connections through the center block, I don't know if there's enough like space actually in between to even allow for much give at all. It's very
All right,
close
cool.
tolerances.
Cool. All right, we'll let Dr. Trom tell his war story and then ask his question.
So many war stories. So, okay, so back when I ran my company, I used a distributor in Tennessee called Tennessee Lab Supply for 2-liter graduated cylinders, which were an integral part of the product that I was selling. And they sold these things for like $15, and then the next closest competitor was like $40. So it was a dramatic cost reduction that I could pass on to my my customers and actually make the kit affordable. So you guys, well, and so what ended up happening is Tennessee Lab Supply just stopped one day, just stopped making these things. And it caused me, I had a huge order, like a 50-unit order, and I had to figure out how to basically produce a product at the price that I had quoted without the inexpensive component that I had expected to be available. So you guys, to some extent, we try to make this experience as close to what happens in the real world as possible, including supply chain problems and trouble with purchasing. And, clearly we ordered the rails the first time around. IGUS says they shipped. We don't have any evidence of it. We went around and around and around and ended up having to order another set of rails. So talk me through a little bit. Clearly there's like, so you guys had a solution, which is like, okay, let's 3D print the rails, which works in the context of this class, right? Because ultimately there's a safety net here. But if you guys had been a real company, and this had happened out in the real world, and you were expected to deliver a functional prototype for a design review that would decide whether you would move forward into getting a contract, how might you guys have handled the situation?
We were actually going to switch our design to use off-the-shelf parts from McMaster.
That would be a pretty significant undertaking though. I think we would have had to do like a whole, I mean, the base plate itself would probably be okay, but it would be a redesign of most of the subsystems above the base plate, most likely, which it isn't a big deal, but it's at the same time, it's kind of like, I don't know, we have the design set up with the IGUS rails, and that's cool, and we like the way it looks, but we have to go through the process kind of all over again. And clearly we redesigned quite a few times, and it just sort of did not seem like the right call. And 3D printing worked, so we were like, all right, we'll stick with this for now.
Going off
Yeah.
oh, sorry,
No,
Professor.
go ahead. I was just agreeing with Derek. So go ahead.
Yeah, so going off of that, additionally, now with like the redesigning of the subsystems, we also would probably switch out the motors and get some new motors, because the motors that we're using in lab weren't able to provide like the proper RPMs and torques that we saw on the performance curves. And so I think that would be one of the bigger steps that we would take in order to kind of redo it, and just finding some other system to restrain it along the linear path, I would say. So pretty much those two little systems.
Okay, gotcha. Yeah. So so which is why I mean, we had this conversation, right? I mean, you guys came to me and you're like, do we redesign this thing, or do we try to find the IGUS rails? And I agreed that a complete redesign, just because we lost a part, probably wasn't a good use of anybody's time. So, but yeah, I think Ria's solution of, or at least what she articulated of let's find a alternative distributor, McMaster car, see if we can use them. Basically, that's what ended up happening to me. I ended up instead of using Tennessee Lab Supply, I found an alternative supplier that was more expensive than Tennessee Lab Supply, but cheaper than what I could get on Amazon, and ended up just kind of biting the bullet. Which of course it's a 2-liter graduated cylinder, which there's not a dramatic difference between them, but it turned out that the one that I ended up buying as the replacement had a different base than the first one, and so I also had to do a redesign of the whole kit to accommodate this different shape base. So I guess where I'm going with this is that this sort of thing happens in the real world, and we try to not have it happen to you guys in Mech 3 because time is limited. But it did, and it was a teachable moment and a good, and I say good in air quotes, good experience. It's a war story that you guys can tell when you're out at job interviews or at my age, right? Telling, your future capstone students about, the time that your IGUS rails got lost. So my other question is, so part of kind of the underlying philosophy for why we have multiple groups working on the same project is we like to get to the end and say, okay, which design decisions were good and which design decisions were not so good. And sometimes you don't know that until you get to the end. With you guys, you've got like the belts, and that's necessitating, I think I'm following correctly, like a motor reversal, right? Like the motors turn and then they stop and then they have to go the other way and they stop. So instead of just continuously rotating. So if you guys had to do it all over again from scratch, seeing some of the other designs that basically just let the motors turn without having to stop and reverse, would you guys go a different route, or do you believe that this is truly the best design for the customer needs statement that we presented?
I would go a different route. The reason, honestly, I originally chose it is I saw a design. I actually think it was Alex's that I really liked that used a similar system, and I was a big fan of it. And B, I'm also, I kind of like the whole X and Y kind of like 3D printer-esque kind of movement system. So that kind of got me pretty excited about it. But after looking at some of the classmates' designs and seeing kind of the continuous rotation ones, I do think those would be easier to implement than this. And this has a lot of quirks and problems that I did not foresee. And I think, yeah, in the future.
Those designs were easier to implement, but I know during our brainstorming phase, we were really fixating on meeting the customer requirement of having adjustable distances. Just made it very easy.
That's true.
Yeah, I just want to chime in and say, when I designed what I designed in Mech 2, I was on the exact same track as what you just said. I still am a big 3D printer head. And that's kind of like all I really knew at the time for like how to move things in an XY plane. And now actually having seen a bunch of them, I also agree that if I were to redesign a shaker table myself, I would probably go with a slightly different design. But I just want to clarify that Dr. Trump's question was not a trick question. He was not trying to lead you towards saying that you would do anything differently. That was a genuine question. And if you truly believe that this is the best design, then we would like to hear why this design has additional benefits over others that appear at surface level to be a little bit more simple.
I'll actually chime in and say that I think a belt-driven system is actually the better design for meeting all of the customer needs. I think configuration-wise, there are some changes I would make to how you guys have things set up and configured here, but that's just from having seen a lot of, I've taken apart an actual and dug into an actual plate reader that has a shaker table mechanism in it and seen that. So I have a different perspective having seen kind of how something similar is done before. But I think a belt-driven system to hit that change in diameter as well as having the variability in speed is the best solution, just some configuration changes would really make this a lot more robust of a design.
So
Right.
would you, oh, sorry, would you toss out the stepper motors and just use like brushed or brushless DC motors and then some sort of mechanism that oscillates back and forth as opposed to
How about,
using software?
how about this? We want to talk about the design changes I would do. Can we stop recording?
We can pause the recording.
All right.
You're the recording guy, right?
All right, we're back to recording. The question I had was, does having the configuration you guys had with those two motors, was it friction that was causing your issues? Or was it a necessity to have perfect perpendicularity or parallelism on all of your sides causing those binding issues that you originally discovered? Does the question make sense?
So
Yeah, that was something that we had talked about previously, like, because it was having so much friction, it was skipping steps, but we also thought it was a little bit over constrained. And I know we had mentioned this like previously during the design phase. So it's constrained by those rails and those guide rails through the center block. So I think getting rid of that completely and figuring out a better system for that would keep it from being too constrained.
Because what you got here, you've got rail, rod. All three of these have to be perfectly parallel. If any of them are misaligned, you get to one end, it's going to stick more on one side, it's going to pinch on one end versus the other. There's going to be one sweet spot where everything is perfect, is spaced perfectly. And for a couple of millimeters around that, you'll have good operation. But yeah, even when you go with two, because you guys ended up with only having two, like only one set of rails and the rods, right?
correct.
So yeah, so you finally got to a point where, okay, cool, we're not binding. But still, I wonder if there was just, you get it misaligned and it wants to pinch in on one side and it pinches and then it starts slipping.
Yeah, and we did see the pinching, especially like near the tensioner system and the knurled bolts. Like the 3D printed sides were starting to come up. So the pulleys were starting to slant a little bit and causing more misalignment.
So yeah, so. Yeah, rigid connections, guys. They're important. And they can mess with you. Hooray, design. So yeah, I don't have anything else.
I do have one more question, which maybe just a different view will help with, but how does the future ODFI integration work with this system? Like where would that go?
So if you go back to the well plate holder, Derek.
Sorry, give me a second here. This one.
Yeah, that's fine. So from our understanding, it was just supposed, so that bottom part, that was supposed to be essentially clear, and the ODFI would just sit in that interface, like right in between those two parts, and it would just shine up, so it wouldn't so it just allow to hit it kind of directly, and there wouldn't be like anything blocking it.
Okay, I got it. So yeah, my initial interpretation of it is you guys have this whole big kind of void space in the middle for the ODFI system to sit on the table and somehow shoot upwards. But okay, that was I wasn't understanding correctly. Okay, I got it. So that the part that I didn't see in the previous picture is where the ODFI system sits.
Okay.
Got it. Okay. I think I'm done.
All right. Any last questions from Alex or comments? Nope. All right. Great job, guys. Congratulations. You're done. You're free.
Thank you, guys.
Yeah, way to go. Good
Thank you.
presentation. I'm sorry I had to dip for like half of it to quench DML combustion. But but thanks for letting me hop back in and prod you guys on some of the design stuff. Great job overall. You know, and congrats.
Thank you.
Thank you.
Appreciate it.
Thank you.
Thank you.